Okay. So, where was I? So, yeah, so I was about to introduce, so last time, we talked about the complex trig functions and complex sine and cosines. And I was about, why I was about to introduce, what was it? Yeah, hyperbolic functions, but I ran out of time. So I will begin from where I stopped. Okay, so first, some identities. Some identities on the complex trig functions and complex hyperbolic functions. So first, I am interested in finding the zeros of the complex trig functions. So complex trig functions and the real trig functions, they share a lot of properties, but there's one thing that was different from the one and the other. So what is it? So complex trig functions, the modulus of the complex trig functions can be greater than 1, right? But on the other hand, the real part, the real complex trig functions, their modulus cannot be greater than. What about the zeros? So for the real sine functions, the zeros of the sine function is the zero of the sine can only be attained when x equals to some integer multiple of pi, right? So sine of pi equals to 0, and sine of 2 pi equals to 0, and so sine of minus pi also equals to 0, and so. But what about the complex sine function? Can I find some other, obviously, the complex trig function is nothing but an extension of the real trig function. So therefore, I am pretty sure that even for the complex sine functions, sine pi, sine 2 pi, sine 3 pi, they all should be 0, right? But can you find some other non-trivial zeros other than this? The answer is no. For the zeros of the complex sine functions, they are exactly same as the real sine function. So the theorem goes like this. For complex sine functions, sine of z equals to 0 if and only if the z is some integer multiple of pi. And for complex cosine functions, if and only if the z is pi over 2 plus integer multiple of pi. Okay, so so if you believe in the theorem, then I can conclude that the sine and for the complex trig functions, their zeros are precisely the same as the real and sine and real cosine. Okay. Okay. So the proof of this is this is our definition of the complex sine functions. 1 over 2i times e to the iz minus e to the minus iz. And from the last lecture, so we found out that sine of z was same as the sine of x times hyperbolic cosine of y plus I times cosine x and hyperbolic sine of y. So this was actually very basic algebra, so I'm not going to repeat this. Okay, so now I want to find the modulus of this complex number. So if you take the modulus, modulus squared, then should be sine squared hyperbolic cosine squared and plus cosine squared, cosine x squared times hyperbolic sine squared, right? Okay. What now? Oh. So, well, for this is a real hyperbolic cosine function, right? And for hyperbolic cosine functions, cosine hyperbolic cosine squared minus hyperbolic sine squared always should be 1, right? That was the definition. That was not definition, but that was the one of most important property for the hyperbolic functions. So I am good. So now I want to replace this cosine hyperbolic cosine squared is to 1 plus hyperbolic sine squared plus cosine squared and sine squared. So hyperbolic sine squared. All right. So now I have sine squared and sine squared hyperbolic sine squared plus cosine squared times hyperbolic sine squared. So sine x squared plus and hyperbolic sine of y and squared. Okay. Okay. All right. All right. Good. Since we are interested in the zeros of the complex sine function, and sine of z equals to 0 if and only if the modulus of the sine of z equals to 0, right? But this is the same as the sine x squared plus hyperbolic sine squared equals to 0. And you have to remember these are just these are real numbers, right? And square of two real, the sum of the two square numbers equals to 0 if and only if this guy equals to 0 and that guy equals to 0, right? So sine x equals to 0 and hyperbolic sine of y equals to 0. And if and only if x is, you have to remember this is not a complex sine function, but this is a real sine function. So x must be some integer multiple of pi. And so when hyperbolic sine equals to 0, so hyperbolic sine equals to 0 if and only if y equals to 0, right? So I'm done. Okay. All right. And well, so the proof for the complex cosine function is almost identical. So I'm not going to repeat this. So I will leave it as an exercise for complex cosine function. Okay. So these are some couple of exercises. They are not a big deal, but complex cosine is sine of pi over 2 minus z, and complex sine is complex cosine of the same thing. So these are easy. Well, so these are some basic identities involving the complex trig functions. Okay. Also I have to add that. So well, the tangent functions and cotangent functions and secant and cosecant. So they were defined by using the complex trig functions, right? So well, for instance, tangent is like defined to be sine over cosine, right? And cotangent is defined to be just reciprocal of the tangent, right? And their definition, well, these type of complex trig functions also exist. For instance, complex tangent is complex sine divided by complex cosine, and complex cotangent is just 1 over complex tangent. Goes like this. So we define complex tangent is sine z over cosine, and complex cotangent is just 1 over tangent, complex tangent, and complex secant is 1 over complex cosine, and complex cosecant is just 1 over complex sine. And also, I strongly recommend you to find the derivative of each of these functions. And as you can expect, their derivatives are exactly the same as the real version of itself, right? So for instance, if you take the derivative of the complex tangent, then it's going to be like complex secant squared. And if you take the derivative of cotangent, and it's going to be minus of complex cosecant squared, right? Those like that. Okay. So exercise number 2 is you're supposed to find the derivative of all these functions. Okay, so these are about the complex trig functions, and there are very similar properties for the complex hyperbolic functions. This time around, I am interested in the zeros of the complex hyperbolic functions. When hyperbolic sine of z equals to 0, and when hyperbolic cosine of z equals to 0. So, for real version of the complex sine function, the only zero of this function was obtained only when x equals to 0, right? What about the complex hyperbolic function? So, the answer is this. Looking at the zeros of these complex hyperbolic functions, they look almost similar to the complex trig function, complex sine and complex cosine. The only difference is the zeros of these functions appears not on the real line of the complex plane, but on the imaginary axis of the complex plane, right? Why is that? So I have such a very interesting properties, but the proof behind this is very simple, because this is my complex hyperbolic sine function, and which is defined to be, if you remember my previous lecture, then was defined to be e to the z minus e to the minus of z, right? So this is definition. So if I replace z by I times z, then this is going to be 1 over 2 times e to the iz minus e to the I minus I of z, right? This is what? This is, I guess this is minus of I times no, sorry. Plus. Yeah, thank you. Yeah. I guess this is precisely I times sine of z. right? So, okay, so therefore, sine of z is just minus I times complex hyperbolic sine of z. Sorry, sine of I of z. Now I understand why the zeros of the complex sine function and complex hyperbolic sine functions are very similar to each other, because this is their relation. Since the only zeros of the sine function was located at when z equals some integer multiple of pi, therefore hyperbolic sine of sine function, the zeros of the sine hyperbolic sine function should appear only on I times some integer multiple of pi, right? So this proof has that. So this is justified, and using the same reasoning, I can also prove the second line of this theorem. Okay. So hyperbolic sine of z equals to 0 if and only if z is n times pi times I. And for cosine, hyperbolic cosine. Okay. All right. Now we're moving on to the next section. So 13.3.7, which is about the complex logarithmic function. So I will begin from some motivation here. Motivation. Oh, yeah, I messed up. Sorry. So what is a logarithmic? What is a log function? So log function is, well, basically that is an inverse of the exponential function, right? And the exponential function. So basically, the range of the exponential function can be almost every complex number, right? So in theory, so you can actually attain every complex number but one as an image of the exponential function. But you are not allowed to have this number as a function value for the exponential function. What is that? The 0. The complex 0 it can never be a function value of the exponential function, right? Yeah, which is very similar to the property of the real version of the complex exponential function, right? So, complex exponential can never be 0. So therefore, in order to discuss the inverse of the exponential function, so the domain of inverse of the exponential function must be all complex numbers but the 0, right? So I have a complex number, and this complex number is a non-zero number. I have some non-zero complex number, and we want to find a complex number W such that e to the W is Z. So I want to find such a complex number W. So how can I do this? The idea is, so if you remember, so your exponential function is e to the x times e to the I times y. So it is very reasonable to consider the polar form of this complex number Z. So I want to write the polar form of the complex number Z, which say that this is R times e to the I times the large data. So this large data, sometimes I call this a principal value of the argument. which is a number between minus pi and plus pi. And also I want to write W to be U plus I times B. Okay, so this relation is now exponential of U plus I times V is, which is e to the U times e to the I times V. And this number should be the same as the R times e to the I times the big data. So in order to be the same, then this number should be R, and this number should be e to the I times the big data. So e to the U is R, and e to the I times V is e to the I times the large data. So it tells us that U must be the natural log of R, and V is data? No, not necessarily. So I mean, so V can be data, but you have many other choices other than data. Actually, V can be data plus any integer multiple of 2 times any integer multiple of pi, right? So 2 times n times pi. So this one should be the most general, right, and most general answer. Okay, so actually, this I have a better name for this. I will just simply say this is an argument of Z. Okay, do you remember this notation? If I say argument of Z, then this does not mean a single value, but this is actually a set of values, right? So therefore, the number W should be the natural log of R plus I times data. And I'm gonna denote this number as natural log of Z. I actually, honestly speaking, so I actually don't like this number. Why? So even though ln of Z looks like a well-defined function, but in fact, this is not a well-defined function, right? This is, well, precisely, this is not a single values function, but this is a multi-values function. You know what I mean? So because the real part of this number is very well defined. So I cannot argue about that, but for the imaginary part, so there's only, you're always free to choose this number n. So this is a infinitely many values function. So this is a so-called the multi-values function. Okay, and in mathematics, if your function is multi-values, then we say the function is not well defined, right? But however, if you do not like the multi-values function, then you cannot study complex analysis. Why is that? Because multi-values function appears a lot in complex analysis. Actually, you have encountered at least once already encountered a multi-values function. What is that? Such as the square root function. For instance, Z is f of Z is, if I say Z is Z to the 1/2, then this is a multi-values function. Do you remember the root of unity? If you remember the root of unity, then you can easily realize that this is a double value function. Oh, well, this which is in fact actually better than the infinite value function. But and also if I say f of z equals to z to the 1/3, then this is a triple value function, and so on, right? So this such multi-value function appears a lot. And how do we deal with this? So if you want to discuss anything about the continuity or the derivative of such a multi-value function, then we actually need to fix this. So this is what you're going to do for today's lecture. Okay. Okay. Oh, before I do that, so some more terminologies. I want to define the large ln of z. So this is defined to be the modulus of the ln of the natural log of the modulus of z plus I times the arg of z. This is the principal value of the argument of z. Well, so in our context, so we say this is the large data, and this number is between minus pi and plus pi. So I have these infinite matrices, but if I choose my data to be a number between minus pi to plus pi, then this is we say this is a capital large ln of z, and sometimes we say the principal value of the natural log. This is okay. All right. So I guess we need a little time to be familiar with this natural function. So I have prepared some couple of exercises. Let me say z is -1 minus square root of 3 times I. And I want to find ln of z and the principal value of ln of z. So what are they? So to find these two numbers, so I want to find the modulus of this guy. The modulus of z is clearly, this is what? Yeah, 2. And the argument, the principal value of the argument is, this is what? So minus, should be negative 3/4 times pi. So ln of z is just ln of 2 plus minus I times plus 2 and pi, and large ln of z is just this one. Okay. Okay, not a big deal. Now let us compare these two values. I want to compare this number and this number. Are they different or are they the same? Well, okay, so let me try to figure this out. So this is simply ln of this is 2 times I, right? And this is just 2 plus I times pi over 2. And on the other hand, this is 2 times ln of square root of 2 plus I times pi over 4. So this is just real natural log. So this is 1/2 of ln of 2. So multiply by 2. So this is just ln of 2 plus I times 2 pi over 2. Okay, good. So this is something that we have expected. But this property is not true for every complex number. So for instance, such as minus, I want to compare these two numbers, 2 times large ln of just minus 1 plus I. Are they the same or are they different? Well, so as always, let me, okay, I will figure this out. So large ln of, so this time around, this is minus 2 times I, right? So, so this is, oh, sorry, I forgot to put the natural log. I'm sorry about this. ln of, so modulus of this, the complex number is clearly 2. And since this is minus I, so the principal argument of this complex number should be like minus I times pi over 2, I guess. Yeah. All right. But on the other hand, this is minus 1 plus I, so 2 times, again, natural log of square root of 2, plus the argument of this is 135 degrees. Or on the other hand, this is plus I times 3 over 4 times pi, I guess. Right? But if I multiply by 2, then this is ln of 2 plus I times 3 over 2 times pi. So they are different. So, so, well, I guess you're all familiar to the natural log function from the calculus, right? And ln of some number to the nth power is the same as n times ln of that number, right? So that was true for every real number, right? But in the world of the complex numbers, they can be different. So why? Why are they different? These two guys are the same, but for number 2, these two guys were different. Why is that? Can you figure this out? Yeah, actually, the answer is very easy. This is the complex plane, and well, I want to focus on this negative real axis. So based on this line, so the argument of the principal argument changes a lot abruptly. So I mean, this is the point of discontinuity at least for the principal argument of the complex number, right? So so this is where argument equals 0, and if I go to the counterclockwise direction, so and I am about to get 180 degrees, but after I pass this point, now my argument is suddenly becomes minus of 180 degrees. So, and for example number 1, this is where 1 plus I being located. And if I take the square of this guy, then square of this guy does not cross this line, right? So therefore, I can enjoy such a very nice property. But on the other hand, for minus 1 plus I, this is where my minus 1 plus I is located. And if I take a square of this, then suddenly this time around, well, by taking square, so this number is actually crosses the line. Therefore, So crosses this line, so therefore I cannot enjoy such a nice property. Okay. Okay, so they are different, but they are the same. Sorry. So I should better. Yeah, this is nice. Maybe you might try to think that I have equality here and I do not have the equality there simply because I persisted to use the principal value of the natural log. What if I change to just ln of complex number? Do I have this property or not? Well, first of all, I will need to clarify the meaning of this equality, right? Because so these two guys on the left and on the right, they are not simply numbers. They are actually the set of numbers, right? So these two, I have this equality actually means that as a set, if these two guys are the same, then I have this equality. But if these two guys are the different set, then I do not have this. I do not have this equality. This is my meaning of the equality of these two multi-valued functions, right? Okay. Okay. Let's do this. So for the left-hand side, first I will need to also make sure what I mean by I to the 1/2. So actually, as I told you before, so I to the 1/2, this is not a single valued number. This is a double valued function, right? So basically, I am supposed to, in fact, so basically, I am supposed to consider, hey, hold on, what is the square root of I? So square root of I is, I guess this is plus and minus of 1/2 plus, sorry, I messed up. 1 square root of 2 plus I times 1 square root of 2. Right? Yeah. Yeah, this is good. Sorry, this is good. Thank you. Suddenly my brain stopped working. So since this is a multi-valued function, so this guy, well, this number actually means I am supposed to consider positive of plus of. First, I will need to consider this value taking union with minus of the same thing. So, well, I told you this is actually a set, right? So if and taking the union of these two, and if taking union of these two is the same as this set, then I have this equality. If not, then I do not have this equality. This is the meaning of this equality, right? This is my convention. Okay, so let's do this. This is what is the modulus of this number? Modulus of this number is 1, and plus I times, and the argument of the principal argument of this guy is 45 degrees or pi/4, and 2 times n times pi, and this is, again, this number is modulus is 1, but this principal argument of this guy is like minus. No. Am I right? No. Not actually. Yeah. Okay. So This is I times pi over 4 to n pi. And this is okay. So I have these numbers and I have that numbers. And union of these 2 points is going to be the set. I have a better idea. Maybe I can write this set as 4 times I times pi over 4 plus n pi. If I do this, maybe I am good to replace these 2 expressions into these ones. Okay. And on the other hand, this time I will use the blue one. So this is 1 over 2 times natural log of 1 plus I times pi over 2. Sorry. I should slow down. And 2 times n times pi. And so this is what? I times pi over 4 plus just n pi. So comparing these two, they are precisely the same expressions, right? So they are the same. All right. So by this point, you might be wondering, do I have such a nice equality? Well, for the log functions, you can always take down the exponent to the bottom. That was considered to be one of the base properties of the log functions. Then maybe you might be wondering, if I use not a principal value of log, but if I use just a regular log, the regular natural log, then maybe I can enjoy such a nice property in the world of the complex log function. But in fact, that is not the case. I want you to verify this non-equality. As I said, these 2 guys are different. Can you see why? On the left-hand side, well, this is nothing but just merely the computation of natural log of -1. So natural log of -1 is what? The argument is minus pi, right? So this is for the left-hand side. So this is just simply I times minus pi plus 2 n pi. But in this case, this is 2 times I times pi over 2 plus 2 n, which is I times pi plus 4 times n times pi, right? So I have 2 n pi here. Well, the sign is a little bit different, but well, actually that doesn't make huge difference. What really makes the difference between these two is this is 2 n pi and this is 4 n pi. So because of that reason, so you cannot have the equality. Okay. All right. Okay. So now we are dealing with some ugly world of the multi-valued functions. So I really don't like this, and I really want to fix this. To fix this, I really want you to introduce the notion of the branch and branch count. The branches of log functions, logarithms. So, well, the point is, well, if you do not want to deal with a multi-valued function, then you actually, I want to change my multi-valued function into a single valued function, but that is not always possible. So actually, well, if you persist to use the domain of log function as the c minus the origin, then you can never be able to have such a nice single valued function. So in order to get a single valued function, then you somehow need to restrict your domain of the log function. That is the idea of the branch of the logarithms. So let me go back to our definition of the log function. So this is our definition of the multi-valued log function. Now what I want to do is I choose just any real number. I would say alpha, and if we, I will just say this is data. Yeah. So if we restrict the data to be between alpha and alpha plus 2 pi, then now my log function is suddenly a single valued function. Ln z is now a single valued function. With domain is, whose domain is the entire complex plane. Well, please allow me to use the complex polar coordinate. Data is so as a picture, so I would say this is my data. The ray, this is not a straight line, but this is half line. So also sometimes I would say this is a ray. The ray that data equals to alpha is here, and if I just get rid of the origin plus this ray over here, then now maybe I can define a single valued function for the log function. If I choose the argument data to be somewhere between alpha and alpha plus 2 pi, and restrict my domain or the complex plane other than this line, then definitely I can define a single valued log function. Okay. And also I have to point out that this is the best I can do. So why? So suppose that I want to somehow extend my domain. Then any attempt to extend my domain, if you want to extend your domain to some point on this ray, then that will clearly make your function discontinuous on this point, right? So you can never, in order to have the single value function, and if you want that function to be continuous and analytic, then continuous, then you cannot have any point on this line, right? As a domain. So such that the function value f of z is one of the values of f of z. This is my definition of the branch. Okay, so what is branch? So suppose that you have some multi-valued function. That can be a double valued function or triple valued function, or that can be an infinite valued function. So whatever your multi-valued function is, then, well, first of all, you have to actually restrict your domain. So suppose that I restrict my domain to some domain D. So D is some open and connected set. And I require this single-valued function, large f, should be first analytic. This is very strong condition. Being analytic is, well, complex, which means complex differentiable, and also must be continuous. So therefore, we require my function, large f, to be analytic and continuous on this set D. On top of that, I also want that the function value capital Z, capital F of Z, is the one of the values of F of Z. Right? So this is our definition of the branch. Okay. So, So for instance, this is my complex plane, and suppose that my multi-valued function is the natural log function, and say that I chose this guy as my domain D. And well, and for this point, this is my point Z. And suppose that I have chosen my function value, large f of z, to be one of the function value of this multi-valued function, natural log of z, right? And once I have chosen this function value f of z, then this will automatically determine all the other point on this domain D of the function large f. Why? Because once I chose the function value of this guy, and my function large f is being continuous and analytic, will actually forces the function value of the other point of this domain, right? So this one is one example of a branch of natural log branch of the natural log of phi. So this one is a very nice example of such a branch. But on the other hand, but not every open and connected set can be the domain of some branch of natural log function. So for instance, if I choose my set D to be something like this analyst, then this guy cannot be a domain of any branch of natural log function, right? So this is can be a domain of ln of z, but this is cannot be a domain of ln of z. So, So I told you I call this guy the large ln of z as a principal value of the natural log of z. But, well, more precisely, I should be calling this guy to be I times arg of z. This is, from now on, I'm going to call this guy as the principal, the branch of ln of z. And what do you think is the domain of this guy? The domain of the principal branch of the natural ln of z is actually, in fact, almost everywhere except this lane emanating from the origin, right? So this one should be the domain of the principal branch of the ln of z. Okay. Okay. And I want to define the branch cut. Suppose that I have a multi-valued function, f, and branch cut is a collection of curves I would say gamma 1 to gamma k. So that the C minus union of these curves is a domain of some branch of F. The interesting thing is, well, for the principal branch of this natural log, so, well, the entire complex plane minus of this curve. So I guess you can easily see this curve. And minus this curve is the domain of this, the so-called the principal branch of the log function. And actually the same is true, well, but actually you don't need to stick to this straight line, right? I mean, well, if I choose this guy to be my rate, then this entire complex plane minus of this curve can also be a branch of some can be domain of some branch of natural log, right? Well, actually, well, you can do like this. Actually, this is totally up to you. So you can take any curve starting from the origin and going and extending to infinity can be, well, can considered to be a line such that the C minus this line is the domain of some branch of the natural log, right? I can do even more. Actually, this line doesn't have to be a straight line. Why? Suppose that I considered this curve going to infinity. Then I'm going to say this curve is gamma, and this entire complex plane minus this gamma can also be domain of some branch of natural log function, right? Well, because, well, for here the argument is well defined, argument is all well defined, and argument is well defined, argument is well defined. So as long as your function does not include the domain of your function does not make a full circle around the origin, then your argument is totally well defined, right? So this one can be also branch cut. The branch cut can be, well, any curve. So it doesn't have to be a straight line. So if your branch cut is a continuous line starting from the origin, then that can be the branch cut of your natural function. Okay. And we also define a branch point, that is common to all branch cut the branch point is the branch of the therefore the branch of the natural function is clearly the origin, right? It's because any branch cut must contain the origin, right? Yeah. Well, this is a little digression. I'm really sorry about this, but this is a multi-valued function, right? I can say, and I want to define a branch of this multi-valued function. If I draw the line starting from the origin and going to infinity along the negative real axis, then I guess this complex plane minus this curve should be the branch of this square root function, right? Well, or I can but in this case, again, this line doesn't have to be a straight line, so your line can be something like this. But this is completely okay branch cut of this function. What about this? Z squared minus 1, everything on it. In this case, now things are getting more and more confusing. In this case, I must have two different branch points. The first one is -1 and the other one is +1. Okay, and what do you think is the branch cut of this function? And branch cut of this function can be any line. Well, maybe like this. Okay. So you can think of you can think of the branch cut and branch point of many different functions. And drawing such a nice branch cut is also actually very interesting topic in complex analysis. But in order to explain this, then I will need to do a little lecture on the algebraic topology. Then I don't want to really do that. So you're going to need some knowledge on the common fundamental planes and the monodromy theorem. But okay, that is another story for another time. Let me just skip this. Okay. So. Suppose that we have chosen a branch, I don't know, Z plus I times theta, but this time around, say that my theta is between so pi over 4 and pi over 4 plus 2 pi. So in this case, my branch cut would be starting from 0 and extending like in this direction. And you are supposed to show that for this branch, ln of I squared is 2 times ln of I. What do you think? Is it right? Agreed or not? Yeah, this is okay. In this, well, so let me compare this with, what was it? Yeah, so previously, so if we do not specify the branch of these functions, then so these two guys were considered to be different, right? But this time around, in this case, they are the same number. They are the same thing. Why? Because this is my branch cut, and this is I, and I square must be here, right? And this rotation along by the counterclockwise direction does not cross the branch cut of this branch. Therefore, in this case, now I can enjoy this very nice identity. Okay. Okay, the next theorem is considered somehow very important, which is about the derivative. Now FB any branch of ln of z. Then my function is analytic, and the derivative of this branch is just 1 over z. Okay, since now finally we are dealing with a single values function. So now we can consider, well, now we can finally discuss about the derivative of this function. So what is the derivative? Okay. All right. So since the natural log function is so very well understood only by using the polar coordinates, so please allow me to use the polar coordinate in the proof of this guy, in the proof of this statement. So ln of z is, well, I will say r theta plus I times v times r theta. And here, so the function u is ln of r, and function v is just theta, which is a number between alpha and alpha plus 2 pi. So now, since we are talking about the differentiability of this function, so I will need to check the Cauchy-Riemann conditions. So if I take the partial derivative of r, which is 1 over r, and u theta, obviously 0, and vr is 0, and v theta is just 1. Okay. Now, do you remember the polar coordinate version of the Cauchy-Riemann conditions? Yeah. I hope so. So this is the polar version of the Cauchy-Riemann equations. So u theta is minus of r times vr. And you can easily check these two equations is true for this choice of functions. And this is true for some reasonably large open domain of this branch. Therefore, I am safe to say this function is the complex differentiable. And also, I am safe to say this function is analytic in this domain. So also, in terms of the polar coordinate, the derivative can be written as, well, e to the minus I theta times UR plus I times VR. So this is e to the I theta, UR is 1 over R, plain and simply 0. So this is just 1 over R times e to the I theta. So this is simply 1 over Z. Okay. Great. Okay. So since we have discussed the exponential functions and log functions, now finally we are about to define the general power function. So maybe some couple of days ago, so while I was like mindlessly watching YouTube, and some people, well, some people, they try to prove that they try to compute this number. What is I to the i's power? Can you actually compute this? Is this number well defined? Yeah. So interesting question. So, well, if you do not know complex analysis, then this is everything is just complete nonsense. But well, since now we can define a general power function, and please allow me to try to compute this number in reasonable manner. Choose any non-zero number, non-zero complex number as a base, and C is any complex number. Then now I can define this guy to be e to the c times ln of z. This is the definition. So, and also you have to, first of all, I want you to notice that on the right-hand side, this function, this expression involves the natural log function. And since we are not specifying any branch of this natural log function, so you should understand this function is also infinitely many values function. Okay. So. Okay, but anyway, so now maybe I can try to compute I to the I. So what is I to the I? This is e to the I times ln of I, right? Okay, so exp of I times well, ln of 1 plus argument of this guy is just pi over 2 and pi. No, something is not right. Okay, great. Okay. And what is this? So this guy is 0, and this is I times I is minus. So this is exponential of minus pi over 2 plus 2 n pi. So n is an integer. Wow, interesting. So, well, I try to take the imaginary number, power of imaginary number, and suddenly it happens to be some real number. Okay, interesting. Okay, so so I have 1 more minute. Sorry about this. These are some properties of the general power function. First, z to the minus c is just z to the c, 1 over z to the c. And this is very easy to see. Well, just looking at the definition of the general power function, you can easily convince this. And if you choose a branch of general power function, so choosing a branch means you choose a branch of this natural log function. If you choose the branch of this natural log function, that is the same as choosing the branch of this general power function. Then this general power function is differentiable, and this is and you can also expect our familiar power for the derivative of polynomials. I actually need to prove this, but I just ran out of time. Okay, I will continue my proof on my next lecture, and see you then.